You've heard a little bit from Thomas earlier about the spatially distributed scratch tests. I'm going to talk a little bit about that and a little bit about spatially or statistically distributed impact tests. So this is a collaboration between lots of different people, some of which are in the room, and what we're trying to do, well, first up is, if we think about worn surfaces, they are generated by the interaction between lots of individual damage events. So these are occurring spatially distributed on a different surface, and it's the interaction between these damages that then builds up and causes the wear. So a couple of different examples there. Sam will well recognise the one on the left from his PhD, as that's image of a wax DRC surface. The one on the right I've just nicked randomly off the internet. That is a abrasive wear. So if we think about our current small-scale wear test methods, there's several of them highlighted there, then they often correlate quite nicely with application performance. You know, on here, for example, down here we've got a micro-impact test, and here on the right, here is a cutting test, and there's quite a nice correlation between the two. On the top, this is a pin-on-disc test from MPL. This is various sort of time steps running forward of a failure of DRC coating, again on tool steel. This is a different load levels, that's reciprocating tests and other things like this. These, as I showed you yesterday, these are SN curves from repetitive scratch, and these are repetitive scratch, again looking at the build-up, in this case of damage and friction. So what do they all have in common? So they all have one thing in common, which is that the deformation is kind of in the same place. It's either in the same track or it's at the same point. So that doesn't quite replicate what is actually happening. The thing we're trying to simulate, it may correlate quite nicely because we're catching enough of the contact. In the impact, for example, we're catching the high strain rate and we're catching the severity of the contact and things like that. But it gives us an option at least to design more closely simulating tests. More complicated, sadly. You don't get one thing for nothing, sadly. But so what industry's really after are lab tests that are going to give them a quick but ultimately reliable test methods that are going to give some indication of their likely performance in these different industrial wear regimes. And they can achieve that by more closely simulating these regimes and therefore matching the mechanisms. That, as Hannah's colleague Mark G has said several times over the years, you don't get anywhere if you don't match the mechanisms in wear testing. So hopefully these new tests that I'm going to talk about today are the sort of things that can give engineers know-how for sensible design. They're quite successful at isolating the individual mechanisms. Real situations are quite complicated. This gives us the option to look at it. And we also, because we have these in situ things in the NAN test, effectively we're monitoring the depth throughout. We have this ability to track how the damage builds up cycle by cycle. And then we can understand defects and things like this in microstructure. So Sam and Honzo at least talked about impact briefly. This is just to remind us what we're doing in our test. In an impact test, we pull the probe off the surface, we fire it in, and it then bounces on the surface, and then loses its energy with a bit of plastic deformation because it's not typically hitting metallic glasses as yet. But I think we should do more of that. That would be quite interesting. And it's a very high strain rate test. So some of these impact tests that Honza showed on alumina, for example, if you look at this, the strain rates are much higher than they are in indentation. Indentation stress strain rates are typically sort of 0.1 per second or 0.01, depending on, and you can go lower than that if you like with an NAN test. It's got decent thermal stability, but it's basically quite low. So clearly it drops as the thing, comes into contact, starts to decelerate, but it still remains high over most of that process. So that's quite a nice high strain rate test. So we talk typically about setting the accelerating distance and the applied load. And the reason why those two things matter is because it's in energy, unlike indentation, in impact, unlike indentation, we're thinking, instead of force, we're thinking actually it's the energy that controls sort of approximately a force times distance relation. The energy that controls what goes on. So, and then you can do this thing repetitively, and this guy here has been a sort of favourite over the years, again, sort of lost in the mists of time where that one came from. So I thought that was a good example, but it's been shown already, so I won't say too much about it, apart from the fact that there's the point that I was using it to try and make is there is quite a nice correlation, even with these repetitive impact tests at the same position, between, in this case it's, I think sand erosion essentially, was it, sand and impact. This one, from Martin's colleagues at Cranfield, now we have a thermal barrier coating, so it's a highly heterogeneous columnar structure. In this case, this is a yttria stabilised zirconia, 7 weight %, and you've got this highly columnar structure, which gives it the strain tolerance. This is an E-beam PVD system, and it's been, in this case, cyclically impacted several times at 3 newtons, and that's generated all this subsurface damage and cracking across these columns, and then material removal. If you look on the right, these are real erosion test results with alumina as the erodent, and you're getting essentially the same mechanisms. I could show other ones as well, and you get basically these subsurface cracks that cut across different columns, and that is one of the major erosion mechanisms. So again, we have quite a nice correlation between the result in the cyclic test at the same position and the actual application. However, it still would be better to actually, this isn't quite what happens in the real world situation. So if we think about these individual impacts, the impact data I showed earlier is a succession of multiple impacts. Each of these individual impacts actually can be analysed at high strain rate. So we typically only have done that for single indentations. So we've either done high strain rate analysis of single indentations and tracked this to get dynamic hardness, that's high strain rate, or we've done a lower resolution version for the repetitive test, because we don't need that same level of data density necessarily for this, or we didn't think we did. So this is some raw data, this is typical. What Steve's done very nicely recently is he's taken a plot like this, and in the new software in P5 now it's a slightly different, it's a different curve actually. Essentially then you can then translate a new function up here, and you translate, and now it tracks everything then as a function of depth against number of impacts. And you very nicely, and you can put your cursor if you like, if you're particularly interested in reading off exactly where it is, but of course you can export the whole lot as well. So you straight away, you're moving away from impacts against time and more towards depth against number of impacts and things like that. So that's a big step forward for the cyclic impact. But what's an even bigger step forward is to say, well actually, what about doing this whole thing at high data density rates? Because then we've got all of these additional metrics to play with, to look at, to understand how the damage kicks in. And that might be useful because we might say, for example, do we see some subsurface damage throwing out, in terms of the output velocity that we don't necessarily see in the depth straight away. So we have a subsurface crack network or something like that. So this is like a screen grab, for example, of the new software. So you can see there's a huge array of different stuff in this plot. It's quite nice, you can run tests more quickly as well, which is another big benefit. So if you think about the number of impacts you typically have done in the past, you might have done a 50 impact test as fairly standard. Now 500 is much more typical, because you can do that in well under 10 minutes, even if it's 1 a second, and you can run them quicker than that if you like. And then this drop down here to analysis results plot then gives you all of these different signals that you could then track as a function of number of impacts. So here we see quite nicely, this is an example of a multi-layer coating system. And what you can see is the depth building up with each number of impacts, and then suddenly at this point it's gone here. But if you look at this dissipated energy here, energy dissipation, so if anything, that's going sooner. So that's an indicator that you might have this sort of early warning system. And we've looked at this a few times, and in some cases there's definite legs in terms of looking at multiple signals together, giving you extra information. So we're quite encouraged by that. And it's also possible to do a high temperature. Yeah. And that capability underpins what we can do now in the multiple test. So we had an idea a few years ago now, and it became ultimately a collaborative project with Cranfield and NPL, and where we could statistically or design statistical arrays of impacts around a central point, and this would replicate what happens in the erosion situation. So how much overlap you get depends on the conditions and things like that in the system you're looking at. So here's an example of some work that Andy did now. This is for a hard coating system for a compressor, part of an engine, so not the hottest part, but nevertheless sort of quite hot part of the engine. And they were quite proud, the guys on the left, about how good this coating was, and they said all we need to do is just tweak it to have better high temperature strength, better high temperature performance, and lo and behold, the one on the right is what they came up with. So let's back to the drawing board, I feel, slightly on that one. Fairly obvious. And the neat thing is that it's exactly the same distribution. And that's what's useful, is you can use the same distribution at different load levels, again and again, looking at statistics, see if you're unlucky, and they're so quick to run. So you build up your... So obviously that's quite visual and it's quite quick. So that's a 10-minute test or something like that. This is an example of some work collaboration Thomas and I got published recently. Here we're looking at different hard coating systems on cemented carbide. Again, it's the same distribution, it's just ever so slightly turned around in the SEM. And what we can see is that this coating system is pretty resistant. You get a little bit of localized damage, but nothing too bad. You can zoom in and investigate that. But you can see this guy here, lots of chipping, substrate exposure here as well. So completely different. And what's absolutely fascinating about these coating systems is, in a cyclic test, this one is better. And it's not just a bit better, it's a lot better. So there is a lot going on in these things. And this correlates, the fact it's better in a cyclic test correlates with its machining performance. But this guy, you'd expect, has different mechanical properties, higher h cubed over e squared. You'd expect it to be better in erosion, and in our test it is. So I think there's a lot potentially going on. We can also look at crack systems and the impact of crack systems on how damage is evolved. So again, here we have 4 different tests with the different numbers of impacts from 50 to 500 on 2 different glasses, fused silica and BK7, and they have different mechanical properties. BK7 is a little bit tougher. Yeah, not immediately obvious that this is the tough one, but it's a little bit tougher and it's a little bit softer, and it has a slightly higher Poisson's ratio. And those, well, particularly this over H over E difference and the Poisson's ratio kick in, and that determines what type of dominant crack system you have in the glass. So you have a radial lateral system dominating in the BK7, and that has a larger, if you like, interaction threshold between neighbouring impacts, and therefore you can cause crack systems to interfere more easily if they're a certain distance apart. The Hertzian cone crack system, which is more dominant in the fused silica, has a smaller interaction system, and you can see quite nicely as these things build up that the sort of spikiness of these guys, then they start to join up, whereas these stay much more localised even on this scale. And that nicely replicates what you see in real erosion tests and gives you a fundamental reason to start to understand why you see it. So we did some work as well. So these are some LEXT images from Hannah, and what you can see here is these are the fused silica system now, and you can see there's, okay, when you're this far apart, these things do not interact. When you get to 60 microns apart, they start to interact. And if you look at BK7 under the same conditions, well, they would start interacting when you're 140 microns apart. So that is the heart of the difference in these two guys. And And there's a lot more to that one as well, but time kicks on. So one of the nice things you can do with distributed impacts is you can change the type of distribution, as we were discussing earlier. You could go towards Gaussian or normal distributions. Another thing you can do is you can change the spacing. You can use similar distributions but change the size, and that changes the amount of overlap automatically. So this is just an SEM from one of these guys, but you can see there obviously there's a much more overlap if we put the same number of impacts in a smaller region. So what does that do in practice? So if we take, in this case this is another thermal barrier coating, gadolinium zirconate now, and this has relatively low fracture toughness. It's got a columnar structure with these strange sort of tops. You can see this is very few impacts, so this is the existing coating structure being maintained. This one now, that structure is being broken up. You see the remains of just the last few impacts. And by the time you get to here, yeah, you see the last few impacts again, but again you're getting even finer structure. So you're getting this build up from these original features, and you're getting basically just break up into very, very small little fragments of ceramic coating. And what's nice is that then if you compare that to what you see on the real erosion tests, apart from the fact this erosion was done with an angular and this is done as spherical, they look exactly the same, give or take. Same very, very small structure built up. So you're replicating the real situation again. Another way you can look at it is you can, again, this is another LEXT. So these are LEXT images of the same gadolinium zirconate. In this case, it's been impacted with a Gaussian or normal distribution on the left and a rectangular distribution on the right. And you can, and I've kind of dotted around just by eye and said, well, clearly that dark region there, that's the bit that most of it's come off. And you can sort of see where these little holes are, where the impacts were. But actually, what you can do, of course, is the instrument saved it, knows exactly where the impacts are, so I can just put them on, overlay them. And there you can see, well, lo and behold, that one is fairly reasonable. You know, that most of those, that region does kind of correlate to a high density. That doesn't. And that is another very interesting thing that replicates what you see in real thermal barrier coatings, that you get damage coming across columns. And that is a very nice example of how it might work there. So this is a limitation of the low fracture toughness TBC. This is the inherent problem with TBC research, by the way, is balancing one of these things, balancing toughness against the fact that the thermally GZO is much better. Again, similarly, you can see on the left is impact, on the right is erosion. Again, same sort of mechanisms. In this case now we're replicating nicely. Subsurface cracking and these flaking in exactly the same mechanisms on the right. So, gives us lots of confidence. So statistical or spatially distributed, I'm not sure what the right word is, random, spatially, statistical, it depends what you want to call it, but if we call it statistically distributed nanoscratch test, as Thomas introduced earlier, we have the idea that the first scratch is in the middle, and then afterwards then the scratches are arranged around that with a set statistical distribution where you choose the size of the width, you choose the number of the region, and you check the load and things like that, and all of those things then go together to determine how much overlap you get. So here's just an example, and the tip geometry kicks in as well, of course. So there's just an example of the sort of thing that you might get just by designing different tests. So what Steve's software does now is it allows us, I think I may have mentioned this yesterday, it allows us to take a particular region and get average results over that region. So we get the average over a certain region, so the mean plus standard deviation, and then we can apply the same thing for each scan, but also all of these different parameters like friction, depth, surface roughness, and that then gives us the opportunity, as I was sort of saying earlier, to potentially use sort of big data approaches to get to the onset of how the wear might progress. So there's some examples on silicon, different types of tests. So this one here at the lowest force, a little bit of this debris, so you're picking up a little bit of debris, but this fractional depth increase parameter stays quite close to 1. In other words, there's not much damage. these other tests are not so much there, but as you jack up this, you get a lot more subsurface damage and you get these huge changes. And you can see the amount of debris that's generated outside the track is quite different. So this silicon is obviously a very, very brittle system. What's nice is then you can look in more detail. So you can use this mean parameter across the track length or across the region of interest. So what's particularly interesting at low force is that we can look, say, at something like this test where there's not much damage and say actually the depth doesn't change too much in the test, the friction seems to go up and down. Well, that's a bit odd. Why is that? And you look at the individual tracks, and this one particularly is more interesting, and you can see nicely transitions between part way along the track. So here you're picking up something either at the edge of the track or even in the track a little bit of subsurface debris, and that's caused this increase in friction, and then it's dropped down again. And so this sort of thing is going on throughout the test, and that's giving you that variability. So you've got some sort of fundamental tribology that is potentially allowing you to look at. So this is now a higher force, longer test. So this one's done with a Gaussian distribution, so this is really to drive the damage near the middle of the thing. And there you can clearly see after a sort of incubation period, then the thing goes and goes and goes. And there you see in this case it's quite high, it's highlighted, the friction's quite high throughout. This is a hard coating system, so this is now a low force, and if you drive this to failure in a single scratch, it takes 400 millinewtons to fail, to have total coating failure and brittle fracture of the silicon. It takes 400 millinewtons under these conditions. In a repetitive scratch, we can generate the same mechanism. We start off here, coating's intact, some point later the coating's partially removed, then you have a chance of brittle fracture of the silicon. And again, you can kind of do these sort of side plots that can be quite nicely as well. You can clearly sort of see how that tracks. And the scratch width is 2 microns, and this is a very sort of small track, so there's quite a lot of overlap. And that initial overlap doesn't do anything, but it just builds up with a number of scans, and you can see, and you can plot all of these things like this, for example. And you can quite clearly see, obviously, this is the point at which it goes. And again, you can see there, and it just, obviously, in this case, the coating has come off in one go. That exactly matches the coating thickness. Once the coating goes, then suddenly that substrate is experiencing these very high stresses, and you get a brittle machining and chipping of the silicon substrate. So you're suddenly exposing it to 10 GPa contact pressures. So these are all very brittle things. So what's also interesting is to look at it for alloy design. I'm trying to design abrasion-resistant alloys. So these are just a couple of bulk alloys, sort of fairly standard things that we've looked at as sort of benchmarking exercise. So on the left we've got stainless steel. So we've got relatively low depth throughout, low friction. Titanium, much higher depth and much higher friction. And you can see this correlation with more brittle debris in the track. This is a more ductile looking scratch track. And you can start, okay, it looks a bit messy, so what I said at the beginning is that you have to take a certain level of complexity to get when you get closer to the applications, but you can clearly see all of these different things going on. Again, the most useful thing, I think, to track the start of the damage is often the surface roughness in the scratch track, because that, I think, is quite a good precursor of things. There's some correlation between high friction and track this roughening in the track. You see here, for example, but some of these have got high friction and they're not correlated. So there's quite a lot going on. So do we expect that? Do we expect steel to be so much better than titanium? Well, from a mechanical property point of view, from an Archard point of view, and the like, or an HRE point of view even, no, not at all. Absolutely not. The titanium grade 9 should be better. But actually, in abrasion testing, titanium grade 9, titanium 6.4 and pure titanium all do worse than 316 stainless steel. The one that does least badly of all of them is the pure titanium, because it's relatively soft. So it doesn't correlate at all. Thomas and I, over the years, have spent a lot of time in different types of tribological tests at different length scales, looking at its performance in repetitive scratch tests, in reciprocating tests. And I think we've kind of got to the point we understand what's going on now, which is that there are native oxides on both alloys in sort of normal environment, and these are protective against wear. So if we do some sort of scratch test, some sort of wear test, some sort of tribological test, sooner or later we will remove those oxides, and then we get the transition to the higher wear regime. So the oxide is, I think it's, it's slightly different anyway on titanium 640. It's quite easily removed on titanium. So what you can see on the right here now is these are nanotribo tests, which we haven't really talked at all about these days, which is a reciprocating wear test option we have, tracking over several millimetres. And what we can see here, if you just look at the friction now, comparing titanium 6.4 at two different lows, 30 and 50 against the steel. Most of them it stays perfectly low throughout, it's fine. But as the, and again, 30 million newtons, this oxide is maintained there. So then the mechanical properties win. The fact it's got it's harder means the track is small and it's resistant. But by the time we do the same test, after a number of cycles, then it's gone bang, and then we've got this transition to this brittle machining because that oxide's been removed. So that's one of the sort of major headaches in using titanium in all of these various different bio applications. You think it's good because it's so good because it matches the stiffness of bone more closely than a lot of other things, but tribologically it's relatively cool. Sorry, that was a sort of side waffle, I guess. So hopefully that's given you some interest in these two new techniques we've developed. They do seem to tell us an awful lot about the progression of wear at small scale. From an applications point of view, it's quite interesting that neither of them are restricted to room temperature. So we have been looking occasionally, in this case with the project with tier coatings, on performance at high temperature. So here's an example on one of their titanium doped MOS2 coatings, and this one was particularly good. It's getting some sort of isolated failures there, but it's doing quite well there. And also we can do high temperature erosion tests, in repetitive impact tests to simulate erosion tests. And again, it's a collaboration. This is some unpublished work as yet with Cranfield. Okay, so thanks very much.